Oh, oh, good. So please, whenever you are ready, we are happy to hear your talk.
Thank you so much for the introduction. And of course, thank you to the organizer for this fantastic event. I think it was a great idea to spend 5 days to celebrate Lou Kaufman's work, great research thoughts and papers that we are lucky that they have been there out there for us to inspire us and provide lots and lots of food for our thoughts. And indeed, I have been very inspired by the wonderful ideas that Lou had. And in particular, this talk is inspired by the paper from 1992, published in the Journal of Knot Theory and Ramification. Notice that is the first volume of JKTR. The paper is a co-author work by Lou Kaufman with Pierre Vogel, and it is titled Linked Polynomials and the Graphical Calculus. And the talk today is based on a joint work with two former students at Fresno State. They were senior undergraduate students when we did the research. Then we take some time to finish the writing. Audrey Baumheckel and Connor Righetti. The paper is available on arXiv, but the title is different than the title for the talk. The title for the paper, in case you want to look for it, is on an invariant for colored, classical, and singular links. So I want to spend a few minutes to mention that particular paper by Kaufman and Vogel, where they extended the Honfley-Petit polynomial and Kaufman two-variable polynomial that are polynomials for classical links. They extended them to four-valent rigid vertex embeddings of graphs in free space. And these extensions use graphical calculi that assign polynomials or invariants. Maybe they are not polynomials all the time, they are actually rational expressions, but they are well-defined invariants that are associated to planar four-valent graphs. And their work allowed to provide different approaches to the two well-known polynomial invariants, and the approaches were via state sum models, similar to how Kaufman bracket is a state sum model for the Jones polynomial up to change of variables. So the states here for the polynomials are four-valent planar graphs, in one case oriented four-valent planar graphs, in the other case unoriented, and of course different calculi for the two polynomials. The four-valent graphs, when we say that they have rigid vertices, we think about them as embeddings of those graphs where the vertices are replaced by rigid disks, and each disk has four strands attached to the disk, and there is a cyclic order of those strands in the neighborhood of each rigid disk, and that cyclic order must be preserved when we apply isotopies for this type of graphs embedded in the free space. And in short, the rigid vertex isotopy of embeddings of such graphs in R3 are combinations of affine motions of the disks together with the topological ambient isotopies of the strands or edges of the graphs. And for those of you familiar with singular links, actually, singular links are in some sense equivalent to rigid vertex embeddings of four-valent graphs. Now I will switch to the research that I have done with my former students, Audrey Baumheckel and Connor Righetti. And that research is related to so-called colored links, and these links were named as such by Francesca Aicardi. They are oriented links together with a coloration. Now, this coloration is a function that is assigned on the set of components of an oriented link, and the outputs are elements of a finite set. Now, those elements can be whatever you wish. Here, let's think about them as colors, or we call them as colors. We call them colors. If the cardinality of the image set for the function is 1, meaning that all the components of the link are colored the same, then you can think of that color link as a classical link. Also, the invariant that we have here will not give us any new information for the Home-Flippity polynomial, or the, well, that is what only one I'm talking about, not the Kaufman two-variable polynomial. We can think of that coloration in a different way besides being a function. This coloration partitions the set of components of the oriented link. So you can think about an equivalence relation on the set of components of the link. And then a color link can be defined as a link whose components have been partitioned into classes. Now, if you have such a color link and then you use the same link as a classical link, but you use different partitions, then the corresponding color links are different. This is very important to note. But you may have functions, so two colorations that are not the same, but they are equivalent. And what we mean by that is there is a bijection between the image sets of the two colorations that preserve the equivalence classes of the set of components of the links that are induced by the coloration. So in other words, colors per se do not matter, or if you use numbers to associate to those colors, they do not matter. It's only how we partition the components of the links is what matters. And then when we want to define an invariant of color links, then we want that to be a quantity that, as most of the time, we compute it by working with diagrams of color links. And besides that, it needs to take the same value on isotopic links. It also needs to preserve that coloration. Should not change the partition of the components of the link. In this research, we also work with singular links. So I will only briefly mention what they are to make sure that I have a more or less self-contained presentation. Singular link is, instead of an embedding in R3, is an immersion in R3 of a disjoint union of circles. We allow only finitely many singularities for those immersions, and we impose that those singularities are always transverse and double point singularities. And then also for singular links, we work with diagrams of them, which are projections of singular links into a plane. And then besides the classical crossings, we have singular crossings that look like four-Bellon vertices. The Reidemeister type moves for singular link diagrams are presented below. Of course, we want to think of singular links as being a larger set than the classical links, or classical links being a subset of singular links. So we have the classical Reidemeister moves, but we also have two types of additional moves where a strand can slide under or over singular crossing. Here we must have both under and over sliding. And another one that allows you to have some kind of a twist at a vertex. And this is what actually determines that we need to regard those vertices as rigid disks, because if you don't have that rigidity, the moves are different. You can remove that twist. But that's not the case. It is not that case here. So those are the Reidemeister type moves for singular links. I put them here only as information. I will not really go over proofs verifying that the invariant that we get are independent on the sides of the Reidemeister moves or Reidemeister type moves for singular link diagrams. The notion of coloration can be extended from colored classical links to colored singular links. In the same idea. Also here you can think of singular links having several components, where a component you just think of traversing the corresponding diagram of the singular link, and when you walk along the strands, when you get to a crossing, singular crossing, you go straight ahead versus turning left or right. And then in that way you can count the components of a singular link. And then an invariant for color singular links must take the same value on isotopic singular links with equivalent colorations. Here are some examples of diagrams of colored links. In the left-hand side, it's a classical link that is colored. It has 3 components, and they are all colored differently, which means that we have 3 classes in that partition. And if I had, for instance, the circle, the component that is just a circle, and then the one that is figure 8 knot, if they were colored the same, then I have just 2 sets in the partition, so that would be a different colored link. And on the right-hand side, you see also singular crossings, also a classical crossing, so this is a colored singular link. This research is related to an invariant constructed by Aicardi and Huyumaya. It is actually, their invariant is an extension of the Humphrey-Petit polynomial of classical link. It's an extension to singular links of that same polynomial. So I will go over how it was originally defined. So they proved that there exists a function, we'll call it here f, which is defined on the set of all diagrams of colored links, and then it takes value into field of rational expressions with rational coefficients, and let's denote the 3 variables that we have there by x, w, and t. This quantity is an invariant of color links and is defined uniquely by the following conditions. We want the value of the unknown to be 1. And if we have any diagram D, this joint union with the standard diagram of the unknown, but we are working with color links. So let's say something about the colors of the component. So if that circle is colored in such a way that color is distinct from the colors of all of the components of D, then the value of that disjoint union can be replaced by dropping the circle and then replacing by this rational expression. And then the invariant is multiplicative with respect to this joint union. So we have this equality for this type of case, for this type of split link. But again, it's important to note, although it's not relevant, it's not prevent you from understanding what comes from here if you miss this information, but it is important for the invariant that we have this equality in the definition, and that actually we need to know what to do when the standard diagram of the anode is colored completely different from the rest of the other components in the disjoint union. So that is what we do. And then, of course, you can continuously apply the type of simplification until you cannot simplify anymore, but then you have a spin relation, as we are so much used to when we work with invariants for knots and links. Notice that I really use colors here for our colored links, and let me explain what we have here. So we have some scalars in front of evaluations of diagrams as standard in knot theory. This is a skein relation, meaning that the diagrams that we have here, 1, 2, 3, and 4, if you forget the colors, they represent outside, the diagrams are identical, so they differ only in a small neighborhood that is represented here. The two diagrams here on the left side that you see that the arcs are colored differently, we want to think about them as being parts of in diagrams that are colored differently or maybe even the same. We just allow that they are colored with any colors. And here we just use red and black. But on the right-hand side, when we use the same color, and to make it easy for us, black, that tells us that these diagrams are parts of larger diagrams that are colored with the same color. The color per se, whether it's black or red or blue, does not matter. What matters is that it is the same color, meaning that those arcs belong, even if they belong to different components in a link, the corresponding components are in the same class of that partition. So that is the definition of the polynomial with those three skein relations. Now it's just a remark, so it's not part of the definition, it's just an observation that the previous skein relation, if we say that these two diagrams represent links or the arcs that we have there are colored the same, then we can combine this term with that term, and you obtain this skein relation. So you have a positive crossing, negative crossing, oriented smoothing. And then this relation together with skein relation 1 that we have in the definition, so those two, tells us that actually if you start with an oriented knot or link whose components are all colored with the same color, then the polynomial, sorry, it's not a polynomial, the invariant that we have here up to change of variables sides with the Hom-Flippity polynomial. So the Aicardi-Huyumaya invariant is an extension of the Hom-Flippity polynomial, and they extend it to colored links. But now you may wonder, okay, what was the point? What does that give us compared to the literature information that we had before? Now, the good news is, or a motivation to continue studying their invariant is that, in fact, it is stronger than Hom-Flippity polynomial when this invariant is evaluated on color links whose components have different colors. So Aicardi has a paper where she provided examples of links that, or pairs of links rather. And in those examples, the Hom-Flippity polynomial does not distinguish those pairs of links. But if you consider those particular links with certain type of coloration, then their invariant does distinguish those links. So that is very good news. Okay. I want to digress a bit and to mention that Aicardi and Huyumaya, actually, they did not search for this invariant. They discovered it while they were studying tied braids and tied links. Tied links are just closures of tied braids. Now, those tied braids are closely related to diagrammatic representations for elements in an algebra that they were very interested in. They refer to that algebra now, the algebra of braids and ties, and in short, BT algebra, I assume B from braids, T from ties. It is a one-parameter algebra. It is unital and associative. I don't have time to go over the presentation of it via generators and relations, but I will only mention a little bit more about what they have done in their research. They introduced the tied braid monoid and also were able to prove analogous Alexander and Markov type theorems for tied links and tied braids. The tied braid monoid is generated by the classical braid generators together with new generators which they called ties. And they represented them as springs between braid strands. Now you can think about those springs as telling you which strands in the braid are colored the same. So that is what the ties represent in this context. And instead of coloring the braids, you can put ties to mention which strands in the braid belong to the same set in a partition, where here the coloration is a function defined on the strands of a braid, and then you assign colors to those strands. And instead of putting colors, you put ties to exemplify which strands are in the same class. So then Aicardi and Huyumaya proved that there exists a family of Markov traces on the BT algebra, and that allow them to define an invariant of tied links using the Jones recipe by composing the Markov trace with a representation of the tied braid monoid into the BT algebra. And tied links actually are in some sense equivalent to colored links, where instead of putting colors to represent which components of a color link are in the same equivalence class, you put ties between them. Only that in the research with my students, we decided that it will be easier to work with colored diagrams instead of ties, because the diagrams get too messy with too many lines or vertices and so on. So in short, the resulting invariant of tied links that Aicardi and Huyumaya arrived at some point is equivalent to the invariant that I'm talking about here. But also the invariant that I'm talking about here is also constructed by them. Only that now I want to go over a different approach to that invariant. All right. I need to remind us about the skein relation that is used when we define the invariant of Aicardi and Huyumaya. So that was denoted by Roman numeral 3. And then one thing that when I was trying to decipher their paper, I was wondering why this relation is not symmetric as I used to see in other invariants for classical knots and links. So I see here positive crossing, negative crossing on the right side, the oriented resolution or smoothing, and on the right side, the positive crossing. There's another relation that we can derive from here if these two diagrams are colored the same, and then get another relation where this crossing is negative, but it's still not symmetric. So then we massaged a bit this relation with other scaling relation that we can derive from this particular relation to get a new scaling relation for the same invariant that looks more symmetric. So as you see here, positive crossing, negative crossing on the right side of the equality. Again, positive crossing and negative crossing. And we were very happy to see the patterns in terms of coefficients in front of the crossings of opposite signs. So I will let you take a look at that. And I will use this relation star, scaling relation star later in the talk. Okay, so our goal with my former students, Audrey and Connor, we wanted to extend the Aicardi and Huyumaya invariant to singular links, but actually we wanted to provide a state sum model for that polynomial in a similar way as Kaufman and Vogel did for the Hom-Flippity polynomial. So again, we had two goals: to extend the invariant to singular links, but also provide a state sum formula for their invariant. And in order to achieve those two goals, we needed to start with the second one. And now I will tell you what we did to extend it to singular, and I should say singular colored links. That is the correct term. So since we want to extend it from a class of colored classical links to something else, you want the invariant to stay the same. In this case, to behave similarly if you compute it from colored classical links. And to make sure that we can differentiate between the two invariants, we decided to denote it differently, and we just use square brackets. So we impose that the value of the invariant stays the same as before if you evaluate it from a diagram of a colored link. But then we need to say what we'll do with the singular crossing. So we impose this scaling relation. So we take a singular crossing. And on the right-hand side, notice that we don't have singular crossings anymore. We have classical crossings and no crossing at all. And we know what to do with these quantities because this is an extension of the invariant f, and we know how f behaves if you have just classical crossing. Okay. But again, you can ask, okay, why necessarily positive crossings there? Why not negative crossings? So you could do either or, either one or two. So notice also the patterns there in terms of the coefficients, the scalars in front. So now we have here negative crossings. Again, those that have different colors for the strengths. The strength can be colored with any color, and it could be even the same. But those that have the same color in black, they have to be colored the same. Doesn't matter what color. And of course, when you compose diagrams, as we do when we work with scaling relations, the coloration has to be consistent. So for instance, I cannot compose this with this unless this one is denoted black and this is denoted red. But again, it means here when we use certain colors, it's just that they can be colored differently, not necessarily one is red and the other one is black. But when you compose them to join them, we have to have consistency. So at the end, they have to belong to the same equivalence class when we think about that coloration as partitioning the components of a link. Okay, so you start with a diagram of a colored singular link. You replace each singular crossing by either skein relation 1 or skein relation 2. And when you are done with that, let me mention here that I use tilde if I work with a diagram of a colored singular link, and I use D if that represents a diagram of a colored classical link. So if I start with a diagram of a colored singular link, and I do this business above at every single singular crossing, then we get an evaluation of the original diagram written as a linear combination of evaluations of colored classical link diagrams. And we know what to do there because we already have that F is an invariant for colored links. But you will ask, wait a second, you can use either 1 or 2. Is the invariant or what you are doing well defined? So one needs to check that. So if you subtract 2 from 1 or 1 from 2, if you subtract 2 from 1 in this case, we get this expression. And then if we go back, the slide we have here is exactly this relation that I mentioned to you, that the polynomial f, actually the invariant f, satisfies this skein relation. So that tells us that what we are doing here, it is well defined, because it doesn't matter if I use relation 1 or relation 2, because actually when you subtract them, the evaluation is 0. So our quantity is well defined. And then we were able to prove that is indeed an invariant of colored singular links. We only needed to verify the invariance under the 2 extra Reidemeister type moves, because since this is an extension of an invariant that we knew is an invariant for colored classical links, so it is independent on the Reidemeister moves 1, 2, and 3. You don't need to check them, so you need to check only the extra moves. So that wasn't too bad to do. And actually extending invariants of classical links to singular links, it is straightforward or in general if you use the standard Vasiliev construction. But our scope was deeper than that. We wanted a new approach actually to the original construction by Aicardi and Huyumaya. And then we were able to find graphical skein relations. And that's the title of my talk. That is primarily what our interest was. So let me explain a little bit what we have here. So those are relations are for evaluating planar graphs that have also colors. You can think of a 4-valent color graph in the same way as a colored link, where now instead of having those crossings, you have flat vertices or flat crossings. And the first skein relation, notice that allows us to remove a twist. The second and third skein relation allows us to remove a bigone. The fourth and fifth does not allow us to remove a triangular face, but it gives us a relation between the difference of something that looks like a type 3 move plot for those singular crossings or vertices. Now I'm thinking about them as vertices, not singular crossings. And then on the right-hand side, we have fewer vertices. So the proof for these skein relations is not complicated. It's just tedious and making sure that you don't make computational mistakes. You use the fact that the bracket invariant, that the bracket quantity is invariant under the extended Reidemeister moves. Actually, we only need, I don't remember now the details if we use also the type 4 and type 5 moves, but we use the fact that it's invariant of color singular links, and we took it from there and you can get these gain relations. The following lemma combined with the previous slide is very powerful, and let me explain what it says. If you start with a connected and colored 4-valent planar graph, if it contains at least one vertex and does not contain a loop or a bygone, it must have some triangular faces. And then using a finite sequence of these moves, either this from left to right or right to left, or the other one below, notice that they are different. The red arc is here oriented differently than the black arc here. So you can apply a finite sequence of such moves such that any planar 4-valent graph that does not have a kink or a bygone, you can transform it so that at the end you will get a bygone. So let me tell you why this is important. We want to say that we are able to use these graphical relations to evaluate any colored 4-valent planar graph. And these relations allow us to evaluate any 4-valent colored planar graph as an evaluation of similar graphs, but with fewer vertices. And then you iteratively you get rid of vertices until you get only a disjoint union of circles. And that is possible because, as you see in 1, 2, and 3, you already get fewer vertices on the right-hand side. But then if you don't have a kink or a bygone, what do? Well, this allows me to slide to get from this diagram to that diagram, or from this diagram to that diagram. And then I have fewer vertices on the right-hand side. So this lemma combined with those graphical relations tell us that we can use this together to these gain relations to write the evaluation of any planar colored graph as a linear combination of evaluations of graphs with fewer vertices, and iteratively applying that, we get the evaluation of the original colored graph as a linear combination of evaluations of these joint unions of colored circles. So then we use certain scaling relations that come from how the original polynomial was defined. I'm looking at the time, I need to go a bit faster, but this allows us actually to say that there exists a unique rational expression associated to a color 4-valent planar graph that satisfies the graphical relations that we had before, and these evaluations. So we can use the graphical relations or the graphical calculi that we have, or calculus, it's only one, and the previous proposition to provide a different approach to the invariant that Aicardi and Huyumaya constructed. And equivalently, that gives us a state-sum model for the AJ invariant. The states in that case are planar 4-valent colored graphs, and then we evaluate those states according to the graphical relations that we had before. So here is using reverse engineering our approach to the invariant by Aicardi and Huyumaya using a state-sum model. And actually, you don't need to rely on singular links anymore. So let's start with a diagram of a colored classical link. Now, instead of saying something about the singular crossings, you say, okay, let me take a positive crossing or a negative crossing and replace them by these formal evaluations, where now you just have these new nodes on the right-hand side. And you do that for all classical crossings in your diagram. And that gives us the evaluation of the original diagram as a linear combination of evaluations of planar four-valent color graphs. As you see, we don't have crossings anymore. We'll just have those vertices. And then those are, you get states. So the resulting planar color graphs are the states of V. And we evaluate them by using our graphical relations that we saw before. And then this approach allows us also to compute our invariant of a colored singular link without relying on the existence of the invariant F for colored classical link. And then from here, assuming that you didn't know that what we have is equal to the original invariant by Aicardi and Huyomaya, you don't need to prove that you have an invariant. So you can prove that in the opposite way as when we derived our graphical skein relations, we assume the invariance under the Reidemeister moves to get the graphical relations. So now it would be backwards. You assume the graphical skein relations to get the invariance. So that is doable. It's just time consuming. And also one can show that the bracket invariant satisfies the skein relations 1, 2, and 3 that Aicardi and Huyomaya had in their definition for the invariant F, which means that our invariant and their invariant is the same, meaning that we provided a different approach to their invariant. And that's it. I wanted to see if I had more, but that was all.